Hello everyone and welcome to the Game Engine programming series where we write the game engine from scratch. In the last video, I gave an overview of the 3D12 pipelines and talked about the root signature and how to create one. We saw that filling in all the necessary data structures for creating a root signature is a rather tedious exercise, and it would be nicer if we had some kind of helper functions that would help us achieve this goal with less typing. Today I'm going to write these helper classes and functions. Further, I'll show you how pipeline state objects are created and write helper functions for those as well. In the 3D12 helpers header file, I'll add a new structure that inherits from the 3D12 root parameter 1. The purpose of this structure is to add a couple of helper functions that would partially fill in the root parameter data for us. For example, let's write a function that will fill the root parameter as root constants. Here, the only relevant data members are passed through the function parameters. These are the number of constants, shader visibility, shader register, and optionally the register space. Then, because we know that the user wants to use this root parameter as root constants, we can set the parameter type to 32-bit constants and fill in the rest of the members with the provided function parameters. As you can see, calling this function with just 3 parameters greatly reduces the number of lines one needs to type to fill in a root parameter structure. In the same fashion, we can define functions that fill in the root parameter as different kinds of root descriptors. In this case, we only need to provide the shader visibility and shader register values. Register space and root descriptor flags are optional. We'll write one function for each type of descriptor, but because the implementation is exactly the same for all 3 of them, I'm refactoring it into a separate private function. Finally, we write the helper function for the last type of the root parameters, which is a root descriptor table. Because this table will point to an array of descriptor ranges, I'm going to add a new structure that inherits from the 3D12 descriptor range 1. It only consists of one constructor that is responsible for filling in the data. The user needs to provide the range type, descriptor count, and shader register, with all other parameters being optional. Going back to the helper function for root descriptor tables, we can take a pointer to an array of ranges, the number of ranges, and shader visibility, and fill in the data members accordingly. Next, I'll add another structure that inherits from D3D12 root signature desc1, which has a constructor for filling in the data members and one function that we can call to create the root signature. I think it's also useful to state the cost of different types of root parameters for quick reference in the comments above. Okay, let's start with the constructor, which takes a pointer to root parameter and static sampler arrays, the number of elements in those arrays, and root signature flags. As I did in the example function, I'm going to deny access to most stages by default. Only the pointer to root parameters array and number of root parameters are required here. Other function parameters are optional. This constructor simply fills these values in their respective member variables. I forgot to put this function within the structure braces, so I need to fix that first. Now we can go ahead and finish the constructor. Next is the create function, which takes the data and creates a root signature. Since using this class is not mandatory, I'd like to have a separate free function for creating a root signature. Then we call it from the create member function here. I'll add a function declaration, and because we are going to need functions from core CPP, I'm going to add a CPP file for helpers here and put function implementations in that file. Since we already wrote the code for creating a root signature in our example function, I can just copy that over to the function implementation here. Let's improve the code so the interfaces are released properly and also rename some of the variables for better clarity. This is pretty much all for root signature helpers. Now we can try and use them to create a root signature. First, I'll add a new function, and in here we use the helper structures. Similar to what we did previously, we need a root signature description, but now I am using our version. I am also going to define the same 3 root parameters using our helpers. Now instead of filling in the data members, we simply use the functions to quickly set the data. The first root parameter is the root constants parameter. So we call asConstants function with the number of constants, shader visibility, and the shader register. Next is the root descriptor, which only needs to know the shader visibility and the shader register. And finally, we have the root descriptor table, which needs an array of ranges. Therefore, we need to define a range, and again, we can do this using the respective helper structure. We can initialize it with the minimum number of needed parameters and use it in the root descriptor table function. That's it for the root parameters. Now we can initialize the root signature description with these root parameters and call its create function to create the root signature. And like we did before, we immediately release the root signature. Now I can call this function during the 3D12 initialization and see if it works. Setting a breakpoint and running the application, we can again inspect the contents of the root parameters and then proceed to create the root signature. We got a valid pointer here without triggering any debug breaks, which means that it totally succeeded, and that always makes me happy, as you can hear it clearly in the excitement of my voice. And it means that we also succeeded in creating root signatures much easier if we look at the difference between these two functions. Now all we did by creating a root signature is tell the API what type of content it will contain. Once we have a root signature, we can set its parameters during rendering. Obviously, that's not going to be in this function, but here I'd like to just explain how the root parameters are set. This code is just for this explanation and will not be executed, and therefore I'll even exclude it from compilation by using a poundif. While recording commands using a graphics command list, first we set the current root signature by calling setGraphicsRootSignature function. Since we are also using a root descriptor table, we need to set the descriptor heap to which the descriptor ranges refer to. At any time, only one resource descriptor heap and one sampler descriptor heap can be set. So our array of descriptor heaps can contain a maximum of 2 elements. Then we can set the descriptor heaps by calling setDescriptorHeaps function using this array and the number of heaps it contains. In our case, we only have one descriptor heap. The sampler descriptor heaps that I mentioned earlier are used for dynamic samplers which can't be included directly in the root signature. Now we are ready to set the root parameters. For our example, we first have the root constants, so let's generate some random constants that we can use. For instance, if we would like to send the frame time and the frame number to the GPU to be used in a shader, we could do something like this. Since the frame time is a floating point value, we need to get its binary representation instead of directly using it as a 32-bit integer. To do that, we take the address of the float and cast it to a U32 pointer and dereference that pointer to get the bit representation of the float as an integer. Now we can call setGraphicsRoot32bit constant function to set each one of our constants. We can also use setGraphicsRoot32bit constants, plural, to set an array of constants. Next is the constant buffer view that we would like to set as the root descriptor parameter. For this we can call setGraphicsRootConstantBufferView and use the GPU virtual address of any constant buffer that we might have. There are variations of this function for other types of descriptors like SRVs and UAVs. Finally, the last root parameter is the root descriptor table, which we can set using setGraphics root descriptor table function and passing it the GPU address of our SRV descriptor heap. Please also note that the first parameter in each one of these functions corresponds to the index of the parameter in the root signature. It's worth noting that the same functions are available for setting compute root parameters as well. Now I can disable this chunk of code and move on to the next topic, which is creating a pipeline state object. In the same way, I'm going to write a function that is only here so that I can go through the steps of creating a pipeline state object. The first iterations of D3D12 had a separate pipeline object creation function for each type of pipeline. Specifically, there is a function for creating a graphics pipeline object and another one for creating a compute pipeline object. We need to fill in a data structure that describes a particular type of pipeline object. For example, to create a graphics pipeline object, we need to fill in a D3D12 graphics pipeline desk structure, whereas for the compute pipeline, we need to fill in D3D12 compute pipeline desk structure. Using these structures, the relevant states of each type of pipeline can be configured. However, the DirectX team quickly realized that this method doesn't offer enough flexibility when a pipeline itself would change. For instance, looking back at the mesh shader pipeline, we see that we would need yet another pipeline creation function to support that. To make creating pipeline objects more generic, a new function was introduced in ID3D12 device 2 interface that uses a pipeline state stream to create a pipeline object. This stream is just an array of different pipeline state subobjects in any order. Each subobject has an enumerated type, which is followed immediately by the corresponding data structure that describes the pipeline state for that type. For example, if we wanted to create a compute pipeline, we could add a root signature type, followed by the root signature pointer, and a compute shader type, followed by a shader bytecode structure. The function that creates the pipeline state is called createPipelineState, and since it's part of ID3D12 device 2 interface, we need to change the return type of our device function accordingly. I'll go ahead and use the latest interface currently available on my machine. Now I can try to create a pipeline state object or PSO. To do so, we define a stream description and a pointer to the interface that will hold the result. And again, we release the object at the end of the function since we are not going to use it here. As I mentioned before, the stream consists of an array of pairs of pipeline subobject type enumerations and their data structures. As an example, let's define a stream here which has two subobjects, one for the root signature and one for a vertex shader. One important detail that we should not forget is to align each structure that contains a subobject to the platform's native alignment size. This is so that each subobject type enumeration starts at an offset within the stream that is a multiple of the native alignment size. This ensures the correct parsing of stream subobjects. To pick the correct native alignment, we can use align_as directive with a void pointer. This will align the structs to 16 bytes on 64-bit platforms and to 8 bytes on 32-bit platforms. Now we can set the data in the stream to whatever root signature and vertex shader we would like to use. Here I'm adding some dummy variables just to advance this example. Next, we can fill in the stream description using the pointer to our stream and the size of it, and pass it to the pipeline creation function. The amount of typing we did here is not as bad as we did for the root signature, But it still needs some effort, since in general we also need to define a lot more pipeline sub-objects than just the 2 that we did here. Moreover, we also need to remember which sub-object enumeration goes with which data structure. To make that easier, I can create a template class and use it to define pipeline sub-objects. The template arguments are the sub-object type enumeration and the data type that goes with it. In addition, we have a default constructor and a constructor that accepts the sub-object data type. I'm also going to define an assignment operator that takes a sub-object data structure and assigns it to the data member in the class. Now I can define sub-object classes for each sub-object type. For our example, I'll define one for the root signature sub-object and another one for the vertex shader sub-object. And this is basically all there is to it. We can try and rewrite the exact same example using the class that I just wrote in a new function. In this case, instead of repeating the pipeline creation code, I'm going to also write a helper function that takes a pointer to the stream and size of the stream and creates the pipeline state object for us. So first I'll copy this code to the helpers header and define one subobject class per subobject type. And instead of typing all these names here, I'll create a macro that will help us define all these types with less typing. This is a variadic macro that takes a name and appends it to the end of D3D12 pipeline state object and passes the rest of its parameter as the template arguments to our template class here. Let's also be a polite programmer and undefine the macro when we are done using it. Now I'll call the macro to define a subobject class for each subobject type. For example, I can make one for the root signature, and as you can see, now we have a D3D12 pipeline state subobject root signature type defined here. So this works fine, and I'm going to just copy all these enumerations and call our macro, carefully pairing each type with the corresponding data structure. Next, I'll write the helper functions that take this stream and create the pipeline state object. In order to offer more flexibility, I'm also going to write a function that accepts the D3D12 pipeline state stream desk. Now we are done and we can use these helpers to create a PSO, and all I need to change here is use the correct namespace. Unfortunately, I can't call this function since it will fail because we don't have a valid vertex shader, but I'm quite confident it will work when we have the needed data. This concludes creating root signatures and pipeline state objects and their helper classes and functions. I hope there was something useful for you here and that you enjoyed watching this video. As always, thank you so much for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!